Hi, in this video we're gonna do semantic segmentation of multispectral images using deep learning. We're gonna do an environmental application in which we detect the percentage of vegetation in an image. This image were taken by a drone that flew over a region, and also the same application could be done for satellite image. So the image shown here that we're gonna use for the training the neural network is a very large image. So unlike other deep learning examples, instead of using a large set of images for training the neural network, we're going to use a single image. And we're going to use the random patch data store to randomly pick segments of the image and feed it to the neural network. And eventually a neural network is going to give us another image of the same size with values in the matrix elements, values representing the categories. And these are the categories that we're going to use. So there are 18 categories. So each pixel is going to have a value from 1 to 18. So that's going to be the output of the neural network. Also, unlike a regular image that has 3 color channels, red, green, blue, we're going to have in this image also 3 additional channels for 3 infrared frequencies that give us additional information about the image. And there's a 7th channel for a mask indicating us which elements of the image are valid. Okay, so let's do the example by opening the live script. Okay, let's put a breakpoint in the first step like this and just hit F5. Okay, so this temp dir is gonna try to make there's a couple of files that a couple of big files that this example is gonna download. The first is the training data, the training images, and the second one is the pre-trained neural network. So the first one is coming from this university, and the second one is coming from MathWorks. Okay, so these are huge files, and in my personal computer I have a solid state drive in C drive, and I don't want the images there. I want it in the regular magnetic disk that has much more data. So that's why they gave us the opportunity to change this. So that's the first thing that I'm gonna change. This is the address, so let's download. This method, it comes with example. This is a folder of the example that I'm working on. I'm gonna give the reference to this example. The reference of this example is in the link in this video. You can click it below. Okay, so yeah, let's download the file. So it's gonna use web save. Create the directory if it is not there. So in my case, I already have it, so it's just gonna skip it. Although you can also download manually and place it in the corresponding folder. Okay, so the second one is the same. It's gonna download the math file, but from a different place. So just gonna skip through this. I already have downloaded, so it doesn't need to get through that. Okay, so let's go to the next one. Let's load the training data. So right now we don't have anything, and this is gonna just load a bunch of variables in the workspace. We're gonna see it in a moment. I'm gonna pause. Okay, it finished loading. We can see that we have test data, train data, test labels, the validation data, validation labels. Okay, so let's try it. One of the issues, you can see that these are huge images. 12,000 by 7,000 pixels, that's humongous. Okay, so we have the channels at the beginning as the first dimension, and the deep learning networks that we use do not support that. We have to put the dimension in the back. So let's just do some pre-processing for that. This is another function provided with example. All it's doing is going through all the first dimension, which is the channel, and putting the first channel into the first channel, but putting a dimension at the end. But there's a problem with this. Notice that in the first iteration we have an image of only one channel. Then we go in the second iteration, and then we have now 2 channels. So each time I'm executing this, it's gonna create a new array, so that's why this complaining. You should pre-allocate this memory, otherwise it's gonna be terrible for performance. And if this is big enough, it can hang your computer literally. Okay, so we're gonna see another example where this is done correctly. So for now, let's just get out of here with a Shift F11, and now let's continue the rest. This takes a while. Okay, no, it didn't take much. Okay, now we should have the channel in the last dimension, and we should be able to confirm it in here. Yes. Okay, now let's take a look at how that training data looks. Notice that the training data here, we just pick the first red, green, blue dimension. We apply his equalizer to improve the contrast. That is an IPT toolbox function, image processing toolbox function. Okay, so we are going to display training data, validation data, and test data all together. Notice that there's no sample dimension because there's only one image for training. Okay, so let's take a look at that. Okay, so here's the training, validation, and test data. Okay, fine. You can see it has some vegetation, sand, and pavement in here. Okay, asphalt. Okay, so now let's take a look at the infrared dimensions for the training data only, dimensions 4, 5, and 6. Okay, so the infrared should be able to give significant additional information for the neural network, and yeah, some frequencies, infrared frequency might have some more details about certain objects. Okay, now let's look at the final channel, which is the mask, that is gonna tell us which pixels in the image are not valid, and we're gonna use it later to ignore them. Okay, now we have these classes. This is one of the variables that came with the math file, and we're gonna create our class names that we're gonna use for the data stores. Okay, so now let's display the labels, the training labels. This is another workspace variable that came with the math file, and we're gonna overlay it on top of the actual image, the corresponding image. Okay, so this is an image from the image toolbox. Okay, so we're gonna again provide the training data image, the infrared channels, and we're gonna use his equalizer to improve the contrast, and then we put the label on top of it with a 0.8 transparency. And the color map we created with this command, and this command is gonna say, okay, we're gonna assign a color to each of the 18 categories. We have 18 categories, so we should be able to see this. It's gonna put one color for each. Okay, now we have the image that is mixing the semantic labels and the original image, and let's take a look at it. Okay, so you can clearly see how objects are being segmented in here. Okay, now we're gonna create a legend for it. We have 18 classes, and we're gonna create we are gonna use this color bar to create the labels, and it needs basically some separation. So we have 18 separations. Let me take a look at this. These numbers provide the separation of the color bar, and we provide the class names, and then we use the color map, this command, to put the actual color into the boxes. Yeah. Okay. So we have tree, grass. There's another one, a third one that is gonna use to determine the vegetation in the image. Okay. And now that we flip the dimension of the training data, let's save it in the math file. And also we're gonna save the training labels into a PNG file. This is a standard image file, so that is gonna be more convenient to use it with a data store soon. Actually in here. For data stores, it's more convenient to use a standard image. because if you, let's just write this, if you use a math file like in here that we are using the math file, this is a non-standard image, so we need to provide a math reader method for reading the data. Okay, so we specify that it has a math extension, so let's take a look at the method and let's put a breakpoint into it so we can see it when it's actually reading data. Okay, so image data stores are the building blocks, one of the building blocks for deep learning, and they are used to feed the data into the deep learning neural network. Usually these data stores are augmented or are dealing with huge amount of files, or like in this case a large image, so they are not going to read everything at once. So when you create the data store, you can see it maybe as a TensorFlow node in a TensorFlow graph or pipeline, in which you specify how the data stores are going to be connected together, and then you realize it, you execute it, reading one image at a time. For example, in here, this random patch extraction is the one that we're going to use to feed the neural network, and it's going to be based on two data stores. One is the image data store that is reading from the original image, and the other one is the one with the pixel label data store. Yeah, and we're gonna provide we're gonna feed small patches, and this is another parameter. Okay, so what's gonna happen is that we create the data store, and the relationships are established. For the pixel, we need to provide the class names and the 18 values, and the image with the label. Okay, so here the relationship is established, but only when we read it is that it's executed. And in here we're gonna read the data store, the random patch data store, and we're gonna get some patches out of it, and that's when this callback method is gonna be executed. Okay, so let's run it, and the breakpoint is gonna be hit. Okay, so now you have this file name where the math file is, so we're gonna load the file, and once we load it, we have a data structure, and one of the fields is called training data, which is the image with the training data. So we're just gonna pull it like this, and we're just gonna pick the first 6 channels, which contains the RGB and the 3 infrared frequencies, but not the mask. It's ignoring here. Okay, so let's just put a breakpoint here and just run it to hit that breakpoint. Okay, now let's display it. It's not really ready to display these patches, but we can see here that we have like 8 different patches, and we have a patch for the input image and the corresponding patch for the pixel label. So basically, by doing this is executing this and applying the same transformation of getting the patch both from this one and from the image and from the pixel label. Okay, so now that we have the data store, now in order to train a neural network, you need the data store that provides you the input data. We need the layers that define the neural network, and we need also the training options. Those are the 3 main parameters to train a neural network and get a trained neural network. Okay, so now we already have the data with the data store. Now we're gonna go to the layers, and for that we're gonna have as an input the size of the patch, 256 by 256 by 6 channels, and that is what this is providing us, the same dimensions. Okay, so now let's use this method that comes with the example, and let's just read it. Run it. Okay, so first we're gonna get an input image input layer of the size of the patch, and then we're gonna create the encoding layers that are gonna use convolution, rectified linear unit, and max pooling. Okay, so we're gonna, in here with this formula, we're gonna determine the number of channels in the current layer, and it's gonna depend on the section. So it starts with 1, so we have 64, and it's gonna increase as the 4 sections keep going. So for the first section, we're gonna take this path because we have to consider the input. For the other ones, the input is just gonna be the previous layer. Okay, so we define the convolution layer. We specify that we have 6 input channels. And okay, for training neural networks, it's important to have an initial value for the weights. If you have a bad initial value for the weights and bias, you could either, it could take more time to train, it might not converge, and give you bad results. So it's important to choose a good initial value. This is something that seems to be still on research, and some of the recommendations are that you have a normal distribution. It could be achieved by using random data or using a Gaussian distribution or other methodology, maybe avoiding too large input values to avoid the explosion of the gradients, or too low to avoid disappearing, or things like that. So it is important to choose well the initial values of the neural network. So here we're using a random, creating random values, and we're just gonna see the dimensions of this. The weights for a convolutional layer is the kernel that is multiplied by the inputs to get you an output. So let's take a look at how this looks. Okay, so the kernel window for the convolution is gonna be 3 by 3. And the inputs are gonna be 6 because of the channels, and the output is 64, which is the outputs that we defining here. Okay, so we multiply these random values by this scalar in here, which is a relatively small value and is inversely proportional is proportional to the inverse of the filter size, which is 3, and directly proportional to the number of input and output channels. Okay, so we're gonna use this formula all over to determine the weights. And then the bias, we're gonna use a value of 1 plus a very small value that depends on some random number that depends on the number of channels. Okay, then for normalization, we're gonna use a rectified linear unit. We use another convolution, use a similar formula. Now the channels is 64 and 64 because they are the same. And finally, if we are in the last layer, we're going to put a dropout. This is another regularization technique to decide randomly with 50% chance to cut some of the connections to do better training, do better generalization of the training. And max pooling is a layer that is good to capture patterns, capture information between windows of the kernels of the convolution. It's more like a trying to capture global feature, while the convolution try to capture local features. Okay, so we keep going, and the second iteration we're gonna go through here. In the previous, because of the max pooling, the number of dimensions are gonna be reduced by half because of this stride. So you can see here that the previous layer is gonna have half the size of the current one, which is increased by twice because of this. So we have now 128. Okay, so it's gonna keep going, and as the layers are created, they're gonna be added in a column like this. You can see now that you have they are appended at the bottom of the column, and it's gonna keep going. Okay, so let's get here, and now we can see that we have much more. Okay, so now let's go to the middle layers. And again, using similar formulas, rectified linear unit, an additional convolution, and dropout for regularization. And now let's decode. For the what this is going to do, this neural network is basically in the encoding phase. It's going to take the input patch, which is 256 by 256, and it's going to increase the number of features and reduce the size of the image. And once it gets to this point, the image is very small and you have the maximum number of features. But now you have to go into the opposite direction to get an image in the output. So the output image is going to be the segmented image. So the values, the number of channels has to end up. So at this point we have about 1,000 features. So that number of channels or features have to drop from 1,000 to 18, which is the number of categories, segmentation categories. Also, the size of the image has to increase from 16 by 16 to 256 by 256, which is the size of the patch. So that's what it's gonna do. You can see here that is the number of channels is reduced by half in each iteration. Again, it's using the same formula for initializing the weights. And yeah, we're going to use a transpose convolution layer. This is from the deep learning toolbox. And yeah, and notice also that when when you create the layer, you're accessing the weights and bias of that particular layer. That's what we have been done with all these layers. Okay, regularization, concatenation layer. Okay, so we keep going, and this is gonna go on for a while, for four phases, 4 sections. Okay, so now that we finished decoding, finish the encoder depth, the decoding phase, then we're gonna put the final layers. And the final layer had to have the 18 categories or segmentation categories. And we're gonna do some basic initialization of the weights based on the number of channels, 64, 19. Okay, and we have a softmax for the output. And finally, we need this layer. This is all the layers that we have used so far are from the deep learning toolbox or machine deep learning toolbox, but this one, a pixel classification layer, is from the computer vision toolbox. Okay, so I understand that this is necessary in order to use the segmentation image processing toolbox segmentation function that is going to take as an input the image and the trained neural network to do the segmentation. So yeah, so this final layer is needed there. Okay, so we're going to append it to the bottom, and now we're going to create a layer graph. So once you have this layer graph, all the layers in sequence are going to be connected one after the other. But if you want additional non-sequential connections, you can do it like this. So we're going to connect some of the layers between them. So notice there are 4 additional connections, and we're going to see them in a moment. Okay, now we have our neural network. Let's analyze it. Let's take a look at how it looks. Okay, we have it. Okay, so you can see here that the input is 256 by 256 and 6 channels. It has all the convolution, rectified linear units, that max pooling that we just saw, and at the end you have the dropout at the end of the 4 sections. And notice how the channels are increasing until they get to 1024 and the image is the smallest. And then you go to the decoder phase. They call it the U-shaped neural network because it goes like in U, goes down and then goes up again in the decoding phase. So now it's going up again from 16 by 16 to the size of the patch, 256 by 256, and the number of features go down from 1,000 to 18 classes of segmentation. Okay, now yeah, okay, so let's close this. Okay, now okay, now we have the layers ready, we have the input data ready, and finally we need the training options. Okay, for the training options, we're gonna use a stochastic gradient descent with momentum, a learning rate of 0.05, 150 epochs, that's a bunch, and mini batch 16. We have a L2 regularization. This is for the momentum algorithm, extra hyperparameter for that optimization algorithm, and we're gonna use a gradient threshold. So if the gradient gets too large, it's gonna be clipped to avoid bad results. Okay, so now we have all that we need, and we just can call the train network command with the data store, which is gonna pick randomly patches from that large image. You have the U-shaped neural network that we just created, and we have the options with some of the hyperparameters. So once we run this, we're gonna have the net output. You just can, the info is optional to get it. You just can say net in here. And this is with an NVIDIA Titan X. This takes about 20 hours. So we're just gonna skip it. And from the second file that we downloaded from MathWorks, we're gonna get a pre-trained neural network. Okay, so this take a while, so I'm gonna pause. Okay, we have the neural network ready, so now let's test it. And for that, we trained it with patches that are 256 by 256, but we're gonna test it with patches of 1024 by 1024. And we're gonna use the validation data. Again, this is a large image, and we're gonna go through all of it with this method that comes with the example. And what this is gonna do is go through the whole image, but the whole image is not necessarily compatible with the size of the image, so we're gonna add some padding into it. Okay, so we have a patch here that has the same base type. It's picking up the base type from the image, and we're gonna use the patch size for that, and the number of channels, which is 6, because the input for the neural network still is 6. Okay, so we're gonna get a padded. We're gonna use the pad array function to pad the image. We get the reminder between the height of the image and the size of the patch, and we just get the padding size. We provide the padding size in here plus the image, and then we get a padded image. So now we can evenly go through the image with the pad size. Okay, now we get the new dimensions. We're gonna notice at this. This is gonna be the output of this function, which is the segmented image. The input is gonna be the validation image, and the output is gonna be the semantic segmented image with the labels. Okay, and we're gonna pre-allocate the memory in order to avoid seeing the same problem that we saw before that that for each iteration we created a new version of the output image. So this is gonna be more efficient to do. Okay, so we're gonna go through all the patches and all the channels, and we're gonna get from the padded image, we get the corresponding chunk of the image like this. And squeeze means basically getting rid of a unitary dimensions. Okay, so this is gonna go through a 6 channels. Okay, let's just hit F5. Okay, now we have the patch, and now we're gonna use this semantic seg, which is an IPT function, computer vision toolbox function, that is gonna use the patch as an input, and the neural network, this is a trained neural network, and the output is gonna be on SININT to be able to display. Okay, now we're gonna get now we're gonna use the predict. We're gonna test the neural network. Okay, it takes a little while, and that patch, this segmented patch, is gonna go to corresponding section of the output, and we're gonna iterate through all the patches of the image, and I'm gonna populate this image. And at the end we're just gonna clip it, because we don't care about the padded section, so we're just gonna use the original height and width to get the output. Okay, so let's run it, and this is gonna take a while. There are some types of machine learning, deep learning problems in which, for example, automated driving, that you care about the efficiency. I mean, how fast you do the computation because you're running real time. But there are other applications like, for example, detecting a tumor, or like this one in which we want to measure the amount of vegetation. These type of applications run in a desktop, are not running real time, so it's okay to go as slow as is necessary to be to do the analysis correct. Okay, so it finished. Now we have the segmented image, and we're gonna take a look at it. And now we're gonna use the mask, the final channel, which has the mask data. And if the pixel is equal to 0, we're gonna multiply the corresponding pixel by 0, because this is an element-wise multiplication of the matrix. And if it is equal to 1, the corresponding pixel is gonna remain the same. So basically it's masking the invalid pixels, because the neural network it can provide values for these invalid pixels, so we need to filter them out. Okay, now let's take a look at how the segmented image looks. Okay, now we can see that there this is one category, this is another one, 2 or 3 categories we can see there. There's some noise, so we're gonna use the IPT image processing toolbox median filter with a kernel size of 7x7 to smooth out that image. So let's take a look. Okay, so now this is a little more smoother, and now this is the output of the neural network, and now we're gonna overlay it the original validation image. Again, we use a hist equalizer to fix the contrast of the image. We're gonna use only this time are gonna use the red, green, blue channels. We pass the segmented image, the output of the neural network. We use a transparency of 0.8 and the color map that we created in the past, and the label overlay function, and this is an image toolbox function. Okay, so now we're gonna get the result. So yeah, so we're gonna test it against the ground truth to see how good it behaves. Okay, again we're gonna create the color map, we're gonna show the image, and we can see that this looks like we had in the training data before. You can clearly see the categories of trees, the grass, the sand. Okay, so now let's take a look at the labels. Okay, and now that we have the result image, the segmented image, and the labels. The labels are, this is for validation, and this is what we got in the output. This is the deep learning results. So we're gonna write it into this file, both of them, just to be able to compare them. So now we're gonna load them again with a data store, a pixel label data store, using the 18 class name and the 18 indexes. So with these 2 data stores, we're gonna use this function, which is from the computer vision toolbox. And it is used to evaluate the accuracy of semantic segmentation. It's gonna compare this data store with this one, and it's gonna get a global accuracy. So now this is gonna go through all the huge image, so this is gonna take a while. Not really as much as training it, but we can see in here that the amount of memory is pretty big. Using somehow a little bit of the GPU, but yeah, but I guess this could be we could use GPU even more to accelerate this a little bit more. Okay, it finished, and the evaluate semantic segmentation method told us that this has 90% accuracy relative to the ground truth, which is pretty good. Okay, now let's compute the amount of vegetation in the image. So let's, using the output segmentation image, we're gonna choose 3 categories that contain vegetation. One of them should be grass, trees, low level vegetation, and grassland. Okay, those are the categories that we're gonna use. Okay, and now we're gonna use the is member so if the pixel, these values could be from 0 to 18, and we can check that real fast. Let's unique. So yeah, these are the possible values in this image. So if a pixel in this image is, for example, these values are in this set, then the value is going to be 1 in the corresponding pixel matrix element. If it is not in the set, it's going to be 0. Okay. And notice that we are flattening the matrix. So we have a matrix here, and now we have a huge vector in here with probably more than 1 million elements. Okay. So now we're gonna count the total amount of pixels. So we know that if the pixel value is 0, it's because it is out of bounds. If you remember, some of parts of the image are out of bounds in here, like this one. We don't want to count those, and the value for that is 0. So we're gonna so if the pixel is in that region, it's gonna give us 0. Otherwise, if it is a valid category, it's gonna give us 1. So these are gonna be another matrix with the valid pixels. So we just can count it to know the number of valid pixels. So we have to flatten the matrix here and then zoom. You could do it like this. This is a way of getting the number of valid pixels, which is this one, but also you could do it like this in the whole matrix. It's the same thing. Okay, so this actually was vectorized already. It was flattened, so doing this should do the same. Yeah, it's the same. So this was not necessary because it was flattened here already. Okay, so this is gonna count the number of pixels that are members of the vegetation set. So we're gonna have a total of vegetation pixels, and also this is a total number of valid pixels, and we just divide one by the other and get the percentage multiplied by 100. So with this we get 51% of the pixels are vegetation pixels. So that is consistent with what we can see in here, that we have some sand, asphalt, and a lot of vegetation. Okay, that's it. Thank you for watching.